Let me just write a message. Okay. Very good. So I hope you can hear me. Yes, give me like some confirmation so I can go on.
Yes, bro.
Okay, great. So let me just make a little summary of what we saw on Friday. Essentially, we introduced the concept of these slow invariant manifolds, okay? In Italian, varietà lenta, okay? So that any initially stiff, high-dimensional system, you see here x dot equals f of x, eventually can be reduced if we constrain it on a slow manifold, okay, to a lower dimensional and non-stiff system, okay? Now, let me just stress the fact that giving sort of analyzing chemical kinetics through this sort of dynamical systems approach, okay, it's very instructive, okay, because it will give us a framework, a theoretical framework, where we can understand not just the time scales involved, but also the structure of the dynamics, as we will see later on. Okay, so it's a very sort of useful technique. Okay, now clearly this slow manifold, you can see my mouse, right? Because I'm moving it with. Can you see it moving?
Sì, si vede.
Okay, so this slow manifold is an invariant manifold for the system. Is very hard to find. Okay, apart from a subset of very simple problems, one of those is the singularly perturbed form. Okay, so if we can start with a nonlinear system and we can actually cast it, okay, place it into this singularly perturbed form where we explicitly, okay, have a parameter epsilon, which is a small parameter representing the ratio of the fast to the slow timescales, okay, then we can say a lot about the system. Now, clearly, you can do this only for very small systems where you can clearly separate the slow and the fast, okay, dynamics. So you can't really do it on a huge level when you have 100 species. Although you can, there are techniques that can be computed, okay, in a computer, okay, can be actually put into the form of an algorithm that can do that. But we're not going to deal with those. So we're going to deal with techniques that you can actually accomplish, okay, or carry out with paper and pencil, okay. So the idea here that we saw is that being epsilon the ratio of the fast to slow timescales, well, you can actually have epsilon go to 0. And this essentially means that the fast transient shrinks to 0. So what we're doing essentially is we're considering every sort of fast phenomenon that's happening in the kinetic system as being instantaneous. Whereas the rest of the system, the so-called outer solution, okay, is being highlighted, okay, as the only sort of existing solution. Obviously, it's going to be a slow evolving solution, and it's going to represent the asymptotic, okay, behavior of the system itself. Okay. If we place epsilon going to 0, then you see that the original system now reduces to a slow evolution, which is represented still by an ordinary differential equation, and then an algebraic constraint. Okay, so this is there is a reduction of order in the original problem from a first order differential equation to essentially an algebraic, okay, system. And this constraint, we called it the slow reduced, or the reduced slow manifold, okay? So this G of F placed to 0, what you can do is you can actually express the fast variables as a function of the slow variables. So whereas we still are solving for the slow variables, okay, you can see here through this ordinary differential system, now we are actually representing the fast variables. We're not solving for them anymore. We're just taking them from this constraint, okay, this slow manifold. So the original system here is reduced in dimensionality because now we only solve for one variable, not two, or one set of variables. And then it's non-stiff because clearly the expression of the fast variables is not there anymore, okay? And the fast variables are simply following the slow variables through this algebraic constraint. We can represent this M0 in this particular way. This is just another notation. So it's a set of points of the plane XS and XF. So it's a locus of point of coordinates XS and XF, such that X of F is equal to H0 X of S. The last thing I said last time is it's not invariant. What does that mean? Well, it's just an approximation of an invariant manifold. Okay, by invariant, again, I mean something that if you start from it and you evolve the original system, you will stay on it, okay? So if you have a locus of points, that will eventually be a trajectory, okay, of the system. M0 is not exactly a trajectory of the system. We'll see that it's quite close to the invariant manifold, which we can actually write at this point for this class of problems. We can actually write as an invariant manifold, which is very good. It's epsilon close, however, to the invariant manifold, but we'll get there. So we talked about the reduced system. Actually, we can go even further, because we can be interested also in the boundary layer. Here, obviously, I mean temporal boundary layer. Let me see if I can write a little bit. Temporal boundary layer. So in the so-called fast, no, that's too much. Wait. Fast evolution, okay. So what do we do? Well, there is a trick that we've already done, okay. Remember the application of the singularly perturbed technique for the consecutive reactions A to B and B to C, okay? So if you go back, we found this, and what we have to do here is define another time, tau, okay, which is rescaled, okay, with respect to t. So we divide by epsilon, okay? So in some sense, well, in some sense, tau, okay, if t is a fast time scale, okay, then if we multiply by epsilon, well, actually it was 1 over epsilon, so we should multiply by t slow over t fast. You see that essentially what tau is it's tau slow. Okay, so tau evolves. So when t, okay, is fast, actually tau is slow. And when t is slow, okay, essentially you're multiplied by 1 over epsilon. So this is actually much larger than tau slow. So what you're doing here is dilating time, okay? You're making what was fast slow, and what was slow really slow, okay? Almost unchanging or constant. So if we rescale time like this, the system can be rewritten as the following. So the slow dynamics, okay, now has an epsilon in front, okay? So because epsilon is very small, okay, this becomes very slow, okay? Because clearly the rate of change, okay? So we'll just write it here. It's very slow. The rate of change of x of s now becomes epsilon slow, so it's very, very slow. On the other hand, dx of f becomes essentially of the order of tau, so it becomes essentially slow. So this, what was fast now becomes slow, and what was slow becomes very slow, okay? And we can do something very similar now, because we can still place epsilon going to 0. And clearly what this means essentially is we're dilating this time. So what becomes very low now becomes essentially constant. So what we have here is that dx of s by d tau now is equal to 0, okay? So that essentially we have that x of s, the slow variables, now stay constant, okay? As a, and let me remind you now, what we're seeing, we're looking at the fast evolution, so we're looking into the initial boundary layer, okay, the very fast evolution, okay? So in the fast evolution now, the overall slow variables now remain constant, okay? And so we can write down, so if we write this constraint, usually it's called f of 0. So to remind ourselves that epsilon is 0 here, these are called fast fibers. They're a bit less interesting than the reduced slow manifold M0, in the sense that these are always of the kind slow variables remaining constant, okay? And therefore the fast evolution now is constrained on the fast fibers. And so we can write something like g of s, x of s is constant, and x of f. Okay? So the fast fibers, you can write them as the locus of points such that x of s, the slow variables, are constant. I will write down, I will try to do a little sketch of what's going on, which is actually corresponding to an existing problem that we're not going to treat. We're not going to treat for lack of time, but it would be very simple, which is called the Michaelis-Menten. I'll write it here. This is just for information, okay? It's just a system that corresponds to a kinetic system of some kind, okay? But it's not really important what it is. It's very easy to actually determine the slow manifold and the fast fibers. So what we have here is our phase space. So this is a two-dimensional system. So it's just one slow variable and one fast variable. So one slow species and one fast species. The equilibrium point is at the origin. And what we have is essentially this. We can find a slow manifold of this kind. This is, again, M0. So this is a reduced slow manifold, okay? So this is what we obtain by placing the system in singularly perturbed form and placing epsilon to 0. So what we have is just the slow evolution. So going all the way down to the equilibrium point. So we'll just add arrows here to tell us that wherever you start, okay, you can start from here, you can start from here, you will end up essentially on this slow, reduced slow manifold, leading you to the equilibrium point. So let's write this equilibrium point, okay? Now, what about the fast fibers? Well, these are always of the kind slow species equals to constant. So in fact, you can actually draw them very, very easily. So these are like vertical lines like these, okay? And so these are F0. So they depend on where you start from. They depend on the initial condition, and they will lead you like this to the slow manifold, okay? So that's a little bit the backbone of the dynamics of the system, okay? This is what you always have, and we will see at least one example of that that's very useful, the chain branching example. We'll get to it pretty soon. So what does this mean? Well, essentially, if you are to integrate the system from this initial condition, for example, you will have something like this. Okay. Now, the trajectory is quite near. It's obviously not going to be exactly on F0, neither on M0, so it will probably be something like this. It may even cross it a little bit, so it will be very close to it. Because neither M0 nor F0 are invariant. That's what I said. So if you start from a point on it, you may not stay exactly on it, but you may remain epsilon close to M0, okay? So again, I mean, if you start from a point even on F0, you may have something like this, okay? And then, so these are the trajectories essentially, okay? First of all, they're parallel. They start parallel to the XF axis. I'll try to be. Of course, I can't draw, okay? So you'll have to draw better than me, okay? So these are all trajectories that are being attracted to the slow manifold, okay? Like this. So by knowing the slow manifold, you see, and the fast fibers, we know a sort of a structure of the dynamics, which is universal. It extends on all the domain, okay? Which is very nice, okay? Now, this is an approximation in the sense that we've placed epsilon to 0, okay? Now, obviously, epsilon is not necessarily 0. I mean, it may be a small number, but it's not 0. And the reason why we placed it to 0 is because we wanted to see how the system was reduced, okay? So the slow system reduces to the slow manifold and the slow evolution. The fast system reduces to the fast fibers and the fast evolution, okay? But what about the actual invariant slow manifold or slow invariant manifold? Where is it? How do we find it? Well, it turns out there is a very nice theorem that, of course, I'm not going to prove, neither cite rigorously, again, due to the guy that we cited last time, Fenikel, in 1979, okay? The theory is called geometric singular perturbation theory. Okay, so SP stands for singular perturbation. Okay. So if epsilon is sufficiently small, so if for epsilon sufficiently small, okay, the theorem actually states that there exists a let me call it slow. The SIM stands for slow invariant manifold. So there exists a slow invariant manifold, which we call M epsilon. Okay. So you can actually write it with the usual notation. So x of f. So it's the locus of points x of f and x of s, such that you can express x of f as a function or as a graph, which we call now h epsilon of x of s, okay? And this is actually invariant, okay? So the theorem actually states that there is a slow manifold, it exists, and this is the most important part, m0, m epsilon is a so-called regular perturbation of m0. Okay? What does that mean? Well, a regular perturbation, it means that m epsilon is really very close to m0. It's actually epsilon close. So remember that m epsilon, you can represent it with the graph h epsilon, and m0, you can represent it with the graph h0. So what that means is that a regular perturbation means that essentially h epsilon of the slow variable, so the graph of this slow manifold is actually representable as a regular perturbation. So it means that h0 representing epsilon equals to 0 is the first term, okay, of a series expansion. And then you will have higher order terms like these, okay, epsilon times h1 x of s plus epsilon squared times h2 and so on. So you see that essentially m0, okay, the reduced slow manifold is just the first term of the slow invariant manifold, which includes infinite terms, okay? That's just the theory. It's very nice because we can actually now not only find a very good approximation of the sim. If epsilon is very small, obviously m0 is a very good approximation of m epsilon, okay? Because clearly all these terms will be very, very small, okay? But it's also very nice because you can find all the other terms analytically. So you can find h1, h2, and so on. How do we do that? So how do we find the rest of the terms? So h1, h2, etc. We say that we enforce the invariance of h epsilon of x of s. What does that mean? So let me remind you, we're trying to find now these terms h1, h2, h3, h4, and so on. So how do we do this? Well, you take the expression of h of epsilon, okay? Sorry. And we know from the definition that the fast species, okay, is equal to h of epsilon as a function of the slow species. So h of epsilon, you can think of it as a graph of any kind, like an algebraic function of some kind, right? what does it mean to enforce invariance? So we have to say that this is actually a trajectory of the system, okay? But we know that from the system, the singularly perturbed system, that dx of f by dt is 1 over epsilon g of f, right? So, very simply, we take this expression here, we derive it just in time. So dx of f by dt is actually dh epsilon by dx of s, right? Times dx of s times dt, okay? And this will be equal to, again, the right-hand side, which is 1 over epsilon gf. But again, if you go back to your singularly perturbed system, this is going to stay as dh epsilon by dx of s. What's dx of s by dt? That's the other ordinary differential equation. So it's g slow, okay? So the right-hand side of the slow equation, x of s. Remember that we're substituting x of f, okay, with x of f here with this expression. So we're going to write h epsilon x of s, okay, equals to 1 over epsilon g of f x of s x of s, okay, h epsilon x of s. And again, where we know that this function here is a regular perturbation, so it has all these terms, h0, h1, etc. Okay, so how do we proceed to find h1, h2, h0, h1, h2? Well, what you have to do is essentially, and we're going to try and do this for the so-called chain branching model that we're going to see next. We're going to substitute these terms, and then you have essentially an equation, okay, where you have on the left, okay, you have this sort of left-hand side, and on the right, okay, you have this right-hand side, okay, and you will have both on the left and on the right-hand side, you will have orders of epsilon. So you will have terms, okay, here, of order 0, so where epsilon does not appear, of order 1 here, where epsilon appears with power of 1, and epsilon appears with power of 2. So what you do is you equate, okay, from left and right, okay, equal orders, okay? So h1, h2, actually even h0, are found by equating equal orders of epsilon. Okay, this is the general theory, but it's going to be clear when we do an actual example. Okay, so right now I have given you sort of the basic theory of singularly perturbed systems. So singular perturbations theory. It's going to be much simpler now that we apply it to an actual hands-on example that we're going to see later on. Although we have applied it already to the A going to B and B going to C, okay? So you can look back now with another kind of approach, okay? But clearly now we have all these geometric sort of constraint like H epsilon, for example, that we can play around that actually represent the asymptotic dynamics of the system. Now, this is clearly not the only technique that we have available, okay? It surely is a technique that is grounded, let's say, on more on mathematics, okay? So it has a theorem. It can prove rigorously that H epsilon is actually invariant and so on and so forth. But before these theories, chemists had other, let's say, simpler techniques that were doing, morally, were doing exactly the same thing, okay? Remember, when you're trying to reduce a system, simplify a system, or actually trying to understand a kinetic system in its time scale, so in its sort of temporal structure, okay, what you're actually doing is trying to find some sort of approximation of the slow manifold. That's what you're trying to do, okay? So you're trying to see how the system evolves asymptotically. Again, because the system is characterized, like these kinetic systems are characterized essentially by very different time scales, an initial very fast transient, and then a very slow evolution where the fast species are actually following the slow species, okay? So in the past, there was a technique called the quasi-steady state assumption, okay? QSSA, okay? This is very known in chemical kinetics as a simplification technique, which is different from the one we've just seen. So it's different from the singular perturbation theory, okay? It is simpler, but you'll see that in the end, what it's trying to do, it's trying to find a function, okay, where you can express the fast variables as a function of the slow variables, which makes some physical sense, okay? So exactly like M0 or M epsilon, okay, we're trying to find, actually, I'll write it here. Again, we are trying to find an approximation of the slow invariant manifold, okay? How do we do this? Well, what's behind the quasi-steady state assumption? Well, suppose that you have a generic kinetic system. How do we write down the evolution of each species? Well, we know that, right? So we write down the evolution of each species. I can write down, for example, some sort of concentration here, or the molar fraction, okay? dxi by dt, okay, will be equal to what? Well, depends on clearly on the chemical mechanism. So let me just sum on all the reactions that are in the system. So let me count them as with K from 1 to NR, the number of reactions of our usual expression of the reaction rate of each reaction. So it will be, well, the difference of the stoichiometric coefficients, okay, of species I, okay, of reaction K, minus the stoichiometric coefficient of the reactants, species I in the reactant side, in reaction K, okay? And then we also have to multiply by clearly the forward and the backward reaction rate, okay? Which has the usual, for example, Arrhenius form, okay? So we remember that, okay? So K is for reactions, I is for the ith species, okay? But if you look at this form, okay, carefully, you'll see that we can actually write it in a very sort of simplified and contracted form. How can we do this? Well, think about what each term here in this reaction, in this right-hand side does. It can do two things. It can actually create species I, so contribute to the increase of its concentration, or it can actually deplete species I, so contribute to its destruction or depletion. So in fact, what the right-hand side of each equation here is a source term that is positive, okay? So we'll just write it down like omega dot I plus minus omega dot I minus, okay? Now, these could be both positive terms. So this is just to highlight the fact that there is going to be an overall positive contribution that creates species I and an overall negative contribution that depletes species I. Okay? Now, usually for certain kinds of species, in particular, if species I is an intermediate species, so some species that is created after the fuel has actually broken up into smaller pieces, okay, or reacted, we have this intermediate species that will eventually oxidize to the final products, like, for example, CO2 and water, okay, in the oxidation of a fuel, of a hydrocarbon fuel, for example. Now, we know that if I is an intermediate, the evolution eventually, well, the initial evolution is very fast, okay? Is fast. So we can try and understand this by looking at the evolution ordinary differential equation that sets the evolution of this species, okay? Initially, so suppose that time equals 0, because the evolution is very fast, so we have, and we'll also understand why an intermediate is very fast. So eventually at the end of these couple of lessons, you will have a very clear idea of why this is happening, okay? But for the time being, what we know that we can understand it, we understood it with this system, okay? Simply because we defined two rate constants, and we suppose that K1 is actually much bigger than K2. Okay? Things are a little bit more complicated than that. In fact, when we talk about chain branching, which is the actual phenomenon, we will actually very precisely understand why this is going on. Clearly, we've understood that combustion starts from from a reactant and ends with a product, and it doesn't go directly from the reactant to the product. It actually first forms a very large group of intermediate species, or so-called radical species, okay? So at time equals 0, because these are very fast, okay? Well, we can suppose that actually the positive source term is much larger than the negative source term, okay? So omega dot plus is much bigger than omega dot minus, okay? Can you still hear me?
Sì, tutto a posto.
Okay. Thank God. Okay. Actually, we can try and understand this by just drawing, okay, an evolution in time. okay? So suppose this is time, okay? And actually we can follow also the magnitude in time of these terms omega plus and omega minus, okay? So at t equals 0, we can say that omega plus I is over here, and we can suppose that omega minus is actually almost 0. Okay, so it's over here. Okay, so what does that mean? It means that essentially, initially, because the rate of change, okay, of xi is the difference between the two terms. At the beginning, we can have a very fast increase, okay? So this slope here is, so this is the xi, okay? So very large dxi by dt. Okay? It's much bigger than 1, okay? And, well, we can also sort of have an initial evolution, okay? So an initial transient where we have this sort of behavior here. So we have a very big sort of large positive source term, okay, and a small negative source term, okay. But because now this evolution is very large, okay, it's very fast. After a short transient, okay, after a short transient, what we have is essentially that these two terms eventually will equilibrate. So we have something like this, okay? The W minus here, the omega minus increases, and eventually you see the two will essentially equilibrate. Now, what does that mean? It means that this term and this term will be equal to 0. So dx by dt will eventually equal to 0. So x will reach a plateau. Okay? And essentially, that sort of behavior means that we will have the occurrence of this very sort of fast transient, which you can measure by this sort of very fast evolution here. Okay, very small transient. So after this, the species may be considered in so-called quasi-steady state. What does that mean? Well, so the dx by dt clearly, if we monitor it here, will go something like this. Okay, it will reach 0. So this is dx. So this is, I'm monitoring the rate of change of the species. Okay, now clearly the difference, okay, will measure how big the rate of change is. Okay, this is clearly a positive, okay, difference. Clearly, if this continues to grow like this and then stays more or less like this, and omega plus stays like this, the two they can be large, okay, but clearly their difference is going to be small. So the rate of change will stay very small. Okay, so what does that mean? It means essentially that the species will evolve. In this particular case, you see the dx by dt is negative, but it's very small. So it will decrease, but it will decrease very slowly, like this. Okay? This is the typical situation that actually happens for, remember, intermediate species. Okay, I hope this is clear. So what I'm trying to do here, I'm trying to generalize, okay, the behavior of intermediate species. And I'm trying to do this by looking at the evolution, okay, the ordinary differential equation that sets their evolution, like two terms that, generally speaking, after a very, very short transient, they will balance themselves out. But that doesn't mean that there is an initial transient where the species is really blowing up. Okay, it actually explodes to high levels. That's why it's called a radical pool. Okay, in general, this is the behavior. So you can explain it by simply following these two terms. You have an initial moment at t equals 0 when the positive term is much bigger than the negative term. So you have essentially a very, very large increase, okay, a very, very large slope, which gradually reduces until it's 0 when the two terms equilibrate after a very short transient. After that, the two terms are maybe different, but only slightly. So the slope, dx by dt, is actually very small, meaning that if this will correspond to a very slow decreasing evolution, okay? Until clearly all of these intermediate species will be depleted, and that means that we've arrived to the equilibrium point, okay? So in fact, if you write the ordinary differential equation, you can write it, for example, as minus, so if we take this equation here, dx by dt equals omega dot plus minus omega dot minus, we can put everything on the right-hand side, okay? And what we can say from this equation, if we look at essentially this picture here at the bottom, okay, we can say that in this region here, which we call the asymptotic region, what can you say about this equation? Well, look at the terms. We have two big terms, omega plus and omega minus, and then we have a very small term. Okay, so essentially, if we look at this, we can say, we can apply a quasi-steady state assumption. Obviously, this is not a steady state assumption, because steady state means that dx by dt is identically 0, so that the species stays constant. Okay, but if you look at this, it's not constant. It's very, very slowly varying. Okay, so we can say that if we take these three terms, we can generally say that the rate of change, being so small, can be considered 0. Okay? So we've applied this so-called quasi-steady state on species xi. We have neglected, okay? This means it's almost 0, okay? We have neglected the rate of change of I with respect to these source terms, okay? So what, you may ask? Well, think about it now. What does that mean? It means that the quasi-steady state assumption translates into, for species I, okay, into this equation. In some sense, we have replaced the evolution, okay, of I, which is obviously originally described by an ordinary differential equation, into an algebraic constraint. Okay, so this you can actually, this function here, omega, you can write it in full clearly. Now we'll just keep it symbolic. Is a function q, okay, of essentially the species, okay? of all the species, which we will write down as a vector x. But remember, we have done this for a set of species because I belongs to the set of species which we call quasi-steady state species, okay? We're not doing it for the fuel or the product, we're doing it for the intermediate species, okay? So what you can actually do here is something very, very, very similar to what we've done with the splitting of the fast and the slow species, okay? What you can actually do here with Q is you can say, well, Q equals 0 is a constraint, but you can actually distinguish between non-steady state species and steady state species, okay, equals to 0. And so in fact, you can actually find all the steady state species as a function, let's call it P, by inverting this and solving for XSS, as a function of the non-steady state species. Is exactly like, if you remember, the fast species were a function, okay, of the slow species in the slow manifold. So this becomes an approximation of the slow invariant manifold. So it's another technique, okay? It's a little bit more, it needs a little bit more experience because you need to know exactly which species you need to apply this to. I don't know from the beginning, but clearly these species that have like the role of a intermediate, you're going to pick those. Now I'm going to give you an example right now, okay? And once you do that, you essentially apply this quasi-steady state assumption. You derive this function Q, and you solve for the steady state species. And this is what you get, X, the steady state species as a function of the non-steady state. So now, essentially, part of your differential system has been turned into an algebraic system, exactly like we know how to do in singularly perturbed systems, okay? Fine. Well, there is also another one, another technique. We're not going to be touching that, but let me just very briefly talk about it. And it's not the quasi-steady state assumption, clearly, it's the partial equilibrium. Approximation. Again, we're trying to find some algebraic constraints, right? That makes sense physically. Now, how do we derive a set of constraints other than applying the quasi-steady state assumption? Well, we can think of the chemical mechanism and all the set of reactions, okay? And I can assume that a subset of these reactions, okay, very rapidly reach an equilibrium, okay? So we're not talking about species like in the quasi-steady state assumption, okay? Where we have these fast species that evolve very rapidly and then they decay more slowly in a sort of quasi-steady state fashion. No, we're saying, look, there is a subset of reactions, okay, of chemical reactions that very rapidly attain a chemical equilibrium. So if we consider K as an index which lies in a group, for example, R partial equilibrium, so that's the subset of all reactions, okay, that go very fast to equilibrium. So we can say that for each of those, okay, the forward and the backward rates equilibrate, okay? And these are your essentially set of constraints. And from those, for example, you can derive a set of constraints where you can express a subset of species as a function of other species. Now, clearly, it's a little bit less convoluted because talking about reactions, you're not really talking about species, which are your unknowns, and therefore you don't really know which species you can write as a function of other species. So you need a little bit of more of a, so this is a little bit less used, okay? But the quasi-steady state assumption is used. And I'll show you where it's used. So this was just a very brief, this partial equilibrium, a very brief sort of, I don't know, flash on it, but we're going to go back now to quasi-steady state. So let's use the quasi-steady state approximation on something that we've already seen, on dissociation reactions. And if you remember, going back with your memory, dissociation reactions, well, first of all, they are reactions that we can globally represent by a reaction of this kind, okay? If we think of it in an irreversible manner, you start from a molecule AB and you split it into its constituents A and B. Very, very important reaction in combustion, especially in the initial part of the combustion where you have essentially fuel molecules being dissociated, okay? But you can also have products being dissociated at very high temperature, okay? Like CO2 or water. CO2 can dissociate in atomic oxygen and carbon monoxide, for example, okay? So these are very, very important reactions. They're also important reactions in combustion, and this you may have seen in propulsion, if you've done some propulsion. They can be important because these need energy, okay? Because clearly to break the bond, you need energy from outside. So they're endothermic processes. So if you have them happening in a combustion chamber, they can be unwanted reactions, okay? Because they can bring down the temperature, okay? So that's just long story short, okay? Now, our idea is, okay, but is this really what's happening, okay? Is AB actually breaking up into A and B, okay? Because if this is the case, and if this is an elementary process or an elementary reaction, then this is actually what's going on, right? So, and this would be ideally, if we look at it, if it's elementary, then this would be unimolecular, right? But we know that, because we already seen this, that the behavior can be either unimolecular or bimolecular. And in fact, it's dependent on pressure, if you remember. And now we're going to try and explain how it's dependent on pressure and why it's dependent on pressure. So in other words, the kinetics of dissociation processes, okay, are pressure-dependent processes. So they're not actually what you would say purely Arrhenius processes. They're not, you can't really write down for processes like these, okay? You can't really write down the Arrhenius form, okay, which is essentially a rate constant times which is clearly in the Arrhenius form times the product of the concentrations, okay? What's the reason for this? Well, we've already seen that there is an explanation for the pressure dependence, which is given by the fact that, in fact, this process here is actually a global process, Okay, so we can write it down here. It's actually global. And by global, we mean that it actually hides sub-processes that are elementary. So the actual elementary mechanism goes under the name of Lindemann mechanism. Okay? And it's a set of elementary reactions. Remember, the elementary reactions are actual collision processes. Okay, so when I write it down, it actually represents collision processes between molecules. And it involves, as we know, third bodies. So what's actually going on is that AB, okay, we'll write it in short here, will collide with a third body, which we call M, through this elementary process, which is reversible. So we have a forward and a backward, so K1 and K2, where essentially nothing really chemical happens. Essentially is just that we need AB to be excited, okay? And M does not participate in the reaction, so we can keep M as M. And AB now becomes like an excited form. So it becomes, in a sense, an intermediate, because now AB can actually dissociate by itself through, once it's excited through this process here, with a rate constant K3 into A and B. So the global reaction is actually hiding the fact that there is a third body that interacts energetically with AB. And you see now that AB star, which is a way of saying that this is an excited form of AB, is an intermediate. Okay? So let's write down the rate of change of the intermediate. So we can write down the rate of change of AB star, okay? And we can do this because now we know exactly the intermediate. So these are elementary, remember, steps. So we can write down for each of those. So the forward step of the first reaction. So K1 AB times M. Clearly, when I'm writing the brackets, I'm meaning I address the molar concentration clearly, as we know. Then we have the backward process, which is K2 AB star. You can still hear me, right?
Sì, sì.
M. And then the final product, which is, the final reaction, which is minus K3. It's a depleting reaction, AB star. Fine.
Scusi, professore, una domanda.
Sì.
Diciamo nel primo step M ai reagenti e ai prodotti è sempre la stessa versione di M oppure M è una versione citata?
Allora, guardi, sarebbe la versione citata, M star, e qua poi dovremmo fare un'altra reazione M star che qua dovremmo mettere, no? M star che si riduce ad M, ok? In realtà questo non serve assolutamente, ok? He's asking whether this is the excited version. This is let's say it's a simplified version. I've omitted the fact that you have a decay now on the left, okay? And so essentially the M star cancels out and you only have M, okay? I don't know if you can see it. So this would be M star, but then you have M star here and M. So this is essentially a global process where essentially it also includes the fact that M decays into M star decays into M plus heat, okay? but it's really unnecessary to write it. So we just consider the standard form of M, okay? It will cancel out, okay? We're interested in AB star at this point, okay? And the fact that there is a third body, okay? So I hope that was clear. But the most important thing here is that, remember that we wrote dxi by dt was equal to a positive and a negative term, okay? Right? In the quasi-steady state assumption. Well, you can recognize this form right here, okay? Where, for example, this is a positive term and these are negative terms, okay? So what we can do is, because AB star is an intermediate, okay? And you can see that AB star now participates, well, it actually is an intermediate because eventually only AB star chemically dissociates, okay, through this second step. So it actually is an intermediate. M star is nothing, it's just an excited form which will then decays in itself, okay? It doesn't split, so that's why we're not keeping the excited version here. We can actually apply the quasi-steady state assumption on AB, okay? And how do we do this? We simply take the source terms, so omega plus and omega minus, and place it equal to 0. Now, this should be approximately equal to 0, clearly, okay? So it's exactly like when we are placing epsilon identically to 0 that we're making, obviously, an approximation. Epsilon, generally speaking, is small, but it's not 0. The same thing here. The rate of change, dAB star by dt, is not identically 0, but it's very close to 0. So what we're doing is we're placing now this approximately to 0, okay? So in fact now we have that famous expression Q, okay, equal to 0, right? So we can express now algebraically AB star, which we have essentially considered as a steady state species as a function of the non-steady state species, okay? So we can solve for AB star and we have something like this. Sorry, this is AB. I copied it wrong. Okay, K1, AB, okay, M divided by K2M plus K3, okay? So we have now an equivalent form of, if you remember in computational singular perturbation form, XF equals H0 XS, okay? But in fact, this is essentially steady state species as a function of X non-steady state, okay? That's what, and we called it P of X of NSS, okay? So now, look at the second step here, okay? What's the overall question is what is the rate of dissociation? Well, the rate of dissociation is the rate at which either A and B is formed, right? So the rate of dissociation is dA by dt or dB by dt And it's actually, look at the third step, this is the second step here. It's essentially K3 AB star. Okay? Now, we've just found a steady state approximation of AB, right? Which is this expression here. So why don't we just substitute it by saying that this is approximately equal to K3, and then the steady state version of AB star, which is, in fact, so K3 now multiplies this function, this group here. And so let me just rewrite it like this. K3, K1 times M. I'm just putting AB out because K2M plus K3, and then I'm putting AB out here. Okay? Now, why is this very useful? Well, we have the rate of formation of the dissociated products, which is the rate of dissociation of AB, okay, equals to, well, a group here, which we can call, for example, a global K, times AB. Okay, so in fact, if I go back to my original global reaction, AB actually yielding the dissociated products A and B with the rate constant K, okay? Well, the quasi-steady state assumption really has allowed us to express K as this group here. Because clearly, dA by dt equals dB by dt, looking at this equation here, is nothing else but K times AB. Okay? So this K here can be used as this group here. So we have K3, K1, M, okay, divided by K2M plus K3. So, if anything, we really have not necessarily expressed the reduced model, but we've actually right now expressed the rate constant of the global reaction, okay, in this particular case, which has this very strange expression here, K. But this will allow us to understand the fact that this will not go up, okay, that these reactions, these kind of global reactions here, which express the dissociation of AB into A and B, are pressure dependent. Why? Well, first of all, remember that from the equation of state, PV is the number of moles times RT. So if we divide by the volume, okay, you see that this is essentially, and number of moles divided by the volume is a molar concentration times RT. So you see that P and molar concentration are clearly related, okay, at constant temperature. So if you increase the pressure, you increase the molar concentration, okay? So now look at this expression for K, because you have two cases, okay? At high pressure, what happens? Well, at high pressure, okay, the third body concentration is high, So M is I. So for example, M, if we think of it as going, well, to infinity in the sense that it's very, very large, you see that the denominator here will get to a point where you can actually neglect K3 with respect to this term here. Okay, so we have that K will actually tend to K3, K1, M divided by K2, M. So this goes, and we have that K is actually a group of constants. Okay, the global reaction, what we've learned for high pressure, okay, again, this is at high pressure. So the global reaction works in this particular case of a high pressure where K is now a constant. Of course, we're thinking in terms of a constant temperature, okay? So here, this temperature here is constant, so that there is a direct link between pressure and temperature and molar concentration. Sorry. So if K is a constant, if we write down again the let me just scroll it up. dA by dt, I'm just rewriting it here for the second time. dB by dt is equal to K AB, right? So K is a constant. So this is a unimolecular process, okay? Because essentially we have found out through the Lindemann mechanism that the global mechanism, okay, behaves like a unimolecular. So there's only one concentration here, so there's only one exponent. So the order is 1, okay? Here it is. On the other hand, what about at low pressure? At low pressure, okay, the concentration is very low, so it will tend to 0, okay? And so the global reaction rate will be K3, K1, M, and then in the denominator we're going to neglect this term. Okay, this is going to 0 plus K3. So you see now that there is a different expression for the global rate. This is divided by K3 M. So it's actually K1M. See here, there's a dependence on the third body concentration, okay? So again, if we now rewrite dA by dt, which is equal to dB by dt, we can write it again as K of AB, but we just saw that K is K1 M times AB. Okay, so you see now that this is, okay, the order is now 2, n equals 2. So this, the reaction behaves as a bimolecular reaction. So you see how essentially the system is pressure dependent, okay? And it's pressure dependent because of this dependence of the reaction rate on the pressure, okay? So in fact, if we summarize, okay, given a reaction which overall has K constant here, a reaction constant giving AB, so dissociation reaction, if we monitor how K varies, okay, with pressure, it will be at low pressure, okay, it behaves like K1 times a molar concentration. And the molar concentration varies linearly with pressure. So you're going to have a linear increase of K. So K is essentially varying like the molar concentration, which varies like P. And this is clearly, as we said, a second order kind of behavior. Okay? For higher pressure, we have a constant, okay, behavior. And so this K will fall off. That's how it's called. This is a fall off behavior because it falls off to a constant value. Okay? So K is constant. And so this is a first order behavior. Okay? So these are essentially reactions that can be written globally. So you can actually write down this reaction here in a chemical mechanism to feed in a computer. So you can consider this in all effects as a elementary reaction, but you should always remember that in fact it's not, okay? It hides the sub-mechanism, okay, which we may or may not write down explicitly. But in this particular case, we have to remember that K doesn't really follow the typical Arrhenius behavior, but it follows this sort of pressure-dependent reaction, okay? The bottom line is that we were able to explain it very effectively through this quasi-steady state assumption, okay, that we did on the intermediate species. So if you remember the Lindemann subsystem, you'll be able to explain why at low pressure the dissociation reactions are in fact bimolecular, and at high pressure they're unimolecular. Okay, so that's one of the uses of these systems, of these techniques. Okay. Under certain conditions, you can also prove that the application of quasi-steady state assumption can be equivalent to placing epsilon to 0 in a singularly perturbed systems. Sometimes the two things are completely equivalent, and this is the case of the following example that I'm going to be giving to you, which is the chain branching example. Now, we'll move a little bit more towards the actual combustion process, okay? So, combustion process. I use the word process here because it's clearly a kinetic process, okay? But it's what we know it to be is a very, very fast or potentially very fast reaction. Sometimes people use explosion. Now, you have to be careful when you use the word explosion. Typically, you have to consider all sorts of fuels, even solid fuels, okay? Or so-called energetic materials. And typically, when you talk about explosions where there is a very fast reaction where you have the production of a large volume of gases as products. So you can also have the combustion of a solid fuel. For example, you can have propellants, solid propellants in a rocket, okay? The two boosters of the space shuttle, or the Vega launcher is propelled with solid propellants, which is a mixture of oxygen and oxidizer and some kind of fuel. So the fuel is generally of metallic nature with aluminium, and of hydrocarbon nature through polymers. Okay, and the oxidizer is a salt of some kind. They're mixed together, but in solid form. And as you know, they will react to form very rapidly to form large volumes of gases. Clearly, in more sort of conventional combustion of gaseous reactants, so fuel and oxidizer, you will have the production of gaseous products. So in this case, it's automatically, let's say, an explosion as well, in the sense that there's never a phase change. So that's the overall kind of word for explosion. So a rapid, let's say, production of hot gases, okay? Usually, we don't just write the word explosion. In English, there's also the word runaway reaction. These are all phenomena that essentially are characterized by a very rapid evolution in time, okay? And in fact, where you have at least one very, very sort of large, very, very short and very fast time scale, okay? And then eventually the system will evolve more gradually towards equilibrium. But eventually, initially you have a very, very large sort of explosion or runaway phenomenon. Now, in combustion, usually there are two ways in which you can actually achieve this kind of very fast runaway, very fast explosion. Okay. Now, these two phenomena are typically occurring concurrently, so at the same time. Okay, but we are going to see them separately. Okay. So one phenomenon, we can call it the chain branching explosion or runaway. Okay. And the other one is called thermal explosion, or again, runaway. Okay. So these two mechanisms are really intertwined, okay, in an overall complex combustion reaction. Okay. Now, the fact that we're going to see them separately, so in this particular case, for example, in this chain branching, we're going to consider the temperature as being constant. Okay. So clearly the temperature is not constant unless you're actually taking heat out of the system in the right amount so that the temperature will stay constant. Okay. So there's some other mechanism whereby the explosion occurs in chain branching, and it's in fact the proliferation, the rapid buildup of intermediate species. That's what we're going to be seeing right now through the chain. Not right now because we finished the time. But on another level, if we don't consider intermediates, we just consider, for example, a very basic one-step reaction, what we'll concentrate is on the thermal aspect. So we know that there is this exponential relationship between the rate of reaction and temperature, okay? And that the rate of reaction is really released globally, so it really increases very close to the highest possible temperature, which is the adiabatic flame temperature. So what we're going to see here, we're going to see in the thermal explosion case, we're not going to bother about how many molecules, intermediate molecules we're going to produce, but we're going to look at the thermal aspect. Is there a particular case where for example, the system explodes if we keep enough heat inside the system? So we're going to be considering a sort of a heat loss mechanism whereby you can actually produce heat through the chemical reaction, through exothermic reactions, or you can actually subtract it, okay? And if you subtract a small amount, the system essentially will grow its own temperature enough that essentially now you have a buildup of rate of reaction, which itself feeds back on the growth of temperature, okay? And that's when you have a runaway. So typically, chain branching as well as thermal explosion are feedback systems, okay, where you have a runaway mechanism that can be introduced. By the way, this is very similar to how, especially the chain branching system, to how virus really spreads around very rapidly. When you see these curves going up exponentially, so rapidly, by exponentially I mean a constant to the power of x, okay? So, so extremely rapidly, then you know that it's a runaway, okay? There is some sort of feedback mechanism whereby the more people get infected and the more will eventually get infected at the second round, because there is a sort of a branching mechanism. We're going to see this next time, starting with chain branching. We're going to apply the singular perturbation case, and then we're going to see the thermal explosion, okay? Sorry that I hope nothing happened until the very last second.